Hello everyone. In this presentation, I'll be presenting our work titled Ergodic Exploration using Tensor Train Applications in Insertion Task. In this work, we model insertion task as a 60 coverage problem where the end effector of the manipulator is actively looking for a position and orientation that lets the peg inserted into the hole. The approach uses human demonstrations to model the reference probability distribution for the exploration. Thus, our approach does not need any specialized sensors. What is ergodic exploration? A robot is set to perform ergodic exploration with respect to a given reference probability distribution if the spatial statistics of the output trajectory of the robot matches the given distribution as time tends to infinity. This means the time spent by the robot at any region in the state space is proportional to the probability mass of that region. What is the difference between a trajectory control problem and ergodic control problem? In feedback trajectory control problem, the goal is to track a given reference trajectory, whereas in ergodic control, the objective is to match the time average spatial statistics of the trajectory to a given reference distribution. Now, the question is how to obtain such an ergodic control. One of the popular approaches to obtain ergodic control is spectral multiscale coverage algorithm. Recall that the goal of ergodic exploration is that the time average statistics of the trajectory of the robot matches the reference probability distribution. In the frequency domain, this corresponds to minimizing the difference between the Fourier series coefficients of the reference distribution and the trajectory of the robot, which is evolving over time. This difference is quantified by a metric called ergodicity metric. Given the system dynamics, a spectral analysis yields us a controller that minimizes this objective. However, a major challenge is that this approach is often not scalable for state space more than 2D. This is mainly because the storage and computation of the Fourier series coefficients and the algebraic operations involved to retrieve the control policy suffer from the curse of dimensionality. We overcome this challenge by using tensor train decomposition technique, a technique from multilinear algebra. This allows us an efficient way to compute and store the Fourier series coefficients involved and perform the algebraic operations to retrieve the control commands in a fast manner which is suitable for online implementation on a robot. Now we apply this for insertion task. We model the end effector holding the peg as a 60-point mass system with position and orientation as the state and the control being the velocity. The human demonstrates the key region in the vicinity of the hole for insertion with different possible grasps of the peg. The position and orientations demonstrated by the human for various grasps is modeled using a Gaussian mixture model. This serves as a reference distribution for exploration. For comparison, we first see how simply tracking the pose samples from the reference distribution performs. We observe that simply tracking the pose samples performs poorly with low insertion success rate. This is because such control strategy does not take into account the history of the visitor states by the robot. Moreover, the controller obtained is not well suited for the implementation on a robotic system. Now we try ergodic control for the exploration. We do this in two ways, one in open loop setting and another in closed loop setting. In the open loop implementation, first we generate a trajectory performing ergodic exploration offline through simulation of a point mass system. Then in the online phase, we track the obtained trajectory on the real robot. Thus, we model the insertion as a trajectory tracking problem. We observe that this method performs poorly. This is due to the fact that the trajectory tracking is not feasible as the peg and the whole setup may collide with each other, which is not considered in simulation. Moreover, history of the actual states of the real robot is not considered either, and hence the exploration behavior on the real robot is not optimal. Finally, we implement ergodic control in a closed loop manner on the real robot. This achieves optimal ergodic exploration for insertion as it considers the history of the state of the end effector. With closed loop ergodic control implementation, we observe that it achieves 100% success rate and takes less time for insertion compared to the other methods. The approach can also accommodate uncertainties in the grasp of the peg, as the human demonstration included different grasps for insertion. In the paper, we highlight other properties of ergodic control that make it particularly suitable for insertion tasks. Finally, we summarize the contribution. We use low-rank tensor train decomposition technique to overcome the curse of dimensionality for closed-loop ergodic control using spectral multiscale coverage algorithm. We provide a formal way to perform ergodic exploration simultaneously in position and orientation using Riemannian geometry. We proposed and demonstrated the benefits of ergodic exploration for insertion tasks. For more details, we refer the viewers to our paper. Thank you for watching.